Okay, so we are going to resume our attempt at constraint optimization from last time. Okay, so very brief overview of what we had was what is the terminology of constraint optimization. We had that constraint was simply written as, right, this was our unconstrained, and constraint became, how did I write it? I said right, I said X belongs to a feasible set sigma. And how did I define this capital sigma? We said we wrote it in terms of equalities and inequalities. So this is our just the way we formulate it. What did we call sigma as? Feasible set. Okay. Having done this, now we'll start with our explanation of the simplest kind of problem to start with, which was equality constraint. One equality and the rest is constraint. Okay. So okay, as before, our objective function is very simple, x1 plus x2, and our constraint equality was simply what? The circumference of a circle. This was our constraint. That's what I had. Yeah, right. Now for this problem, we can, it's good to draw a geometry for this. Right, this is my C1x is equal to 0. Right. What was, we calculated grad C1 x. What was that? 2x1, 2 times x1, x2. And geometrically this was what way? Always pointing radially outwards, right? So we'll take few points like this. If I take 4 points over here, A, B, C and D. So this is the way grad C points, and then I can also look at grad fx, and that turns out to be, what does it turn out to be? 1, 1, right? df by dx1, df by dx2. This is a constant vector, so it's always pointing in the same direction. Okay. Then the other thing is what are the contours of constant f of x? So this is very simple to see. What are the contours? Straight lines, parallel lines with a slope of minus 45 degrees, you can say. So these are the contours of constant f of x. Okay, and which way is f of x increasing? Towards the top right or bottom left? It's increasing towards the top right. So we know already looking at this diagram that the solution is going to be point A, because that's the place where f of x is the minimum, and yet I am on the constraint, right? So without solving this problem in any formal way, I know that the solution is A. So this is a very simple problem. I don't need any of the machinery of constraint optimization for this, but this will give me the geometric intuition to formulate how to solve this problem in general. So, what is the observation that we can make at the solution? So, at A, if you were to try to come up with some geometric relation between grad f and grad c, you can see that they are parallel to each other or anti-parallel. So, you could simply write it as grad f of x star because that is the solution, is lambda times grad c 1 of x star, right. This is this true at points B and D? No, it is not true, but it is true at point C. Okay. And that is in a way okay, because when we did our unconstrained optimization, what was our condition for stationary point in unconstrained optimization? Grad f of x star equal to 0, and that was true at a maxima as well as a minima. So, nothing special over here. We are starting with the simplest. What kind of a condition would you call this? It could be a necessary condition, it is not going to be sufficient. So, this is the analog of that. I am coming up with a necessary condition that a minima point should show. Point C, if you were to characterize it, what is point C? It is actually a maxima. This is a point at which f of x is maximized while satisfying the constraint. So, it is not that much of a surprise that grad f is 0 at that point also. But let us try to now formalize this a little bit more. Okay, so how does this work? Okay, let's draw our geometry once again. So, now let me ask you a question. Let us say I am at some point, and obviously I am going to assume I am not at the true solution. Okay, so I am at I have to assume that I am at a feasible point. Okay, so this I mentioned this earlier, this is a very important assumption. We are going to assume that at every point of the algorithm I am at a feasible point, I am not somewhere out in deep space. Okay, so I am at a feasible point. In this case it means that I am on the circle. Okay, so C1x equal to 0 is always going to be satisfied, that is a given. Okay, so now the question is, I want to move to a better point. Okay, so I want to move okay. So, let us say I am at a feasible point x and I want to move to a point x plus s. Okay, obviously s is a vector of the same dimension. Okay. So, C1x, what is the value of C1x? 0, because I am at a feasible point. I have moved to a new point C1, I mean a new point x plus s. What will C1 be? Has to be also 0, because I am only going along feasible points. Okay. So, this is already telling me something that should happen. If I apply Taylor's theorem to C1, so Taylor's theorem, so C1 x plus s, first term will simply be C1 x, second term will be grad C1 x transpose multiplied by s. This is our simple, right. And so, this tells me what? There is no option but grad C1 transpose s should be 0. Grad C1 transpose x s is equal to 0. Okay, that is how it looks algebraically. Geometrically, what does this mean? That means this direction s in which I am going must be orthogonal to grad C1, and grad C1, as you saw in the previous slide, was always radially outwards. So, I know this. Okay. So, let us now pick a point. Let us say I am at this point. This is my current point x. Now grad C1 at this point again is going to be radially outwards. Okay. So what is this telling me about where S can lie? The perpendicular line to this, right? So let's take another color here. I think green may not be very visible, so switch to orange. Is it visible? Yeah. So let's say for S, that means S has to be of course S, if I'm saying S is along the tangent, what further condition you think will apply on S? Should be very small, infinitely small, because if I make it big I will leave C1, which I don't want to do. But of course all of this is in the limit as for small quantities, so I can approximately say that this is going to be fine. Is this enough, or something else also needs to be looked at? So far I have commented on feasibility, but why am I doing this whole exercise? To go to a better position, right? So that has not yet been brought into the picture. So to bring this into the picture, better point means what? F of, right? So f of, so let's write that as better. F of x plus s should be less than f of x. Only then is it an improvement, right? So this is what is required. Okay. What trick do you think I can apply to simplify this further? Same trick, which is Taylor's theorem, right? So Taylor's theorem will give me f of x plus s is equal to f of x plus grad f transpose s. Okay. What does this imply? Obviously grad f transpose s should be less than 0, so that f of x plus s gets reduced with respect to f of x. So grad f x transpose s is less than 0. Okay. Does this remind you of something that you have already studied? It's another word for saying S is a descent direction, which makes sense. Okay. But that's the algebraic way of looking at it. Let's go back to our diagram over here. Which way was my grad f? Grad f was always in the same direction, 1, 1, right? So if I use the red color for grad f, and here comes the interesting part, right? So here is my grad f. And what is my condition? Grad f, what? Grad f transpose s should be less than 0. So how do I quantify this? The geometry of grad f transpose s less than 0 is basically a half plane, a half space. So if I were to draw something like this, okay, let me try the highlighter. Basically this region, right? In this region, if I take a candidate vector that looks like, let's take black again. Oops. Let's call this S. Okay. Does this S satisfy this condition of decrease of the function? It does, because any S that I take in this pink shaded region will satisfy grad f transpose S less than 0. So this is a suitable candidate, right? But does this S which I have drawn, does it satisfy the feasibility condition? Yes or no? No, because grad C transpose S is not 0. But it gives us a clue that of the two possible directions that I had for S, which one should I take? The one in the pink region, right? So you can see geometrically it's very easy to see. So it's saying that this direction over here, this is where you should go, because it is satisfying both the conditions. In fact, there's a certain nice similarity with gradient descent. I'm going exactly in minus grad so far. Okay. So The two conditions that I need to keep in mind at this simultaneously are grad C1 transpose is equal to 0 and grad F transpose S is strictly less than 0. Okay, remember I want this to be strictly less than 0, because if it is not strictly less, then the function is not improving. Then I am just literally going around in circles. So this is strict. Okay, is this clear what we did over here? We're just looking at the various things that have to be satisfied. There are only two things that I need to worry about. One is the constraint be satisfied. That means I stay on the feasible set. That gave me that I should move orthogonal. So look at the geometry. I should move orthogonal to the gradient of the constraint. That makes sense, right? Because if I move orthogonal to the grade, supposing I am walking on a hill and I move orthogonal to the gradient of the hill, doesn't my height remain the same? So same thing, if I am moving orthogonal to the gradient of the constraint, that means the constraint value is remaining the same, which is what I am doing. So I've got my grad C1 transpose S is 0 in plain words, and I want the function to improve. I already know what that means, it should be a descent direction. So grad F transpose S is less than 0. Putting it together, I've got, if I were at this point, I have a legitimate non-zero direction in which if I go, my function will decrease. So I can keep doing this in small steps, right? We are currently not talking about an algorithm. We are only talking about what is possible. We will subsequently come to your simplest algorithm for constraint optimization, but right now we are not getting into it. Okay. Now, having understood this, what is the next logical question we should ask? When to stop? I can keep doing this, but I should now come up with a signature of when to stop. Okay. So, move more to the right. When do we? Another way of saying this is when does improvement stop? That's the question that we are asking. Okay, so here is our circle. This looks more like an ellipse. Okay. Let's take this point over here. So grad F is here, grad F is here, and my grad C1 is here, grad C1 is here. So this is grad C1, grad C1, grad F, grad F. Okay. What were the two conditions that we had? Grad C1 transpose S should be equal to 0, right? That means I am, if I were to draw a plane like this, I am in the which part? Which part? Bottom left, top right. So let's write this, grad F transpose S less than 0. Which part am I? Bottom, right? So if I were to use the highlighter here, this is where I need to be. And for the lower point, grad F transpose S, again it will be the bottom. So this is where I need to be. Okay. And the second condition was grad C1 transpose S is equal to 0. Yeah. Which tells me I have to be on this line, right? Is it possible if I am at either of these 2 points? These points were points A and C, right? This was my point A, this was my point C. Are these two conditions being satisfied at either A or C? I hear a no. Anyone for a yes? Take a guess. Are they being satisfied? No, because it's the strict inequality which is stopping us, right? So they are not satisfied. and that's because of the strictness of the inequality, right. So, we've basically got a signature for when to stop, right. At the previous point you saw that the location which I had drawn, it was possible to find a feasible direction. Now I can't do that anymore. So, graphically, what can you say is the relation between grad f and grad c at either of these 2 points? They again seem to be either parallel or anti-parallel, right. So, I can quantify this as when grad f is equal to say some lambda 1 times grad c1, okay, then further improvement is not possible. Okay. So, this is you can think of this as a signature for a stationary point, right. Now, you have already a good background in something like steepest descent, right. So, if you were thinking now in terms of an algorithm, hopefully if you implement it correctly, if you start from some intermediate point, let us say over here by this cross, is it likely for you to end up at the point C, or is it more likely you will end up at the point A? You will end up at the point A, because from this cross point over here, if you follow sufficient, if you follow the first condition, which is grad f transpose is less than 0 descent direction, you will never go towards C, because that would that the analog of that is gradient ascent, which we obviously will not be doing. So, currently we are not talking about which algorithm we will use, but intuitively you know that whatever algorithm, common sense algorithm you use will decrease the function value. I will end up close to point A, right, and point A is actually the true solution. Nevertheless, we can see that mathematically this condition is being satisfied at point C as well, and that is okay, because this is the signature for a necessary condition. So, that is okay. Okay. Now, the way the literature progressed, we want to make a kind of a one-to-one analogy between constraint optimization and unconstrained optimization. In unconstrained optimization, stationary point is grad f equal to 0. In constraint optimization, is grad f equal to 0 the solution? No, there is this lambda business coming over here. So, motivated by that, to draw a one-to-one analogy, people defined a new function. The word you would have heard of many times, it's called the Lagrangian. Okay. So, let us define that. So, it is L as a function of 2 variables x and lambda 1. Very simply, f of x minus lambda 1 c1x. I have defined it like this. This is called Lagrangian, and this is called the Lagrange multiplier. Correct. So, now if you got the definition of this Lagrangian correct, now if I ask you what is the signature of a stationary point, what would you say? Grad L with respect to which variable? X, right. So, stationary point so I will indicate that I am taking derivative with respect to x by putting it as a subscript. Okay. And actually there will also be a optimum value of lambda. So, I am saying that this is the signature for a stationary point. Okay. So, now you can see that it has a kind of a one-to-one symmetry with unconstrained optimization and first order condition. First order necessary condition for unconstrained optimization was grad f equal to 0. First order necessary condition for constrained optimization is grad Lagrangian equal to 0. So, it is on even footing. Okay. Any questions so far? Right. So, all we have done is we have looked at feasibility and improvement. these are the two legs on which my algorithm, I mean my intuition is moving forward. These are the two things I want to work out, okay, and that's given me two very simple conditions. What is the constraint over here? I am working with first order Taylor theorem, so obviously I have to make small steps, but that's okay. Okay, so let's move on.